You get a wave pattern because this photon is really not a particle, but it's a probability distribution. It only has a probability of existing at any particular place. Because of that, it has a certain amount of probability of going through this slit or going through that slit. Well, it goes through both because it has a probability of going through one or the other. I mean, both. It goes through both. It interferes with itself on the other side. You get a wave distribution on the screen behind you. Now, physicists saw that and were much confused by it, so they did an experiment. They said, well, let's see what's really going on in those slits. So they measured, they put a device in there, a sensor, let's say. They could tell you which slit that photon went through, or did it actually go through both. When they did that, the photon just went through one slit, didn't make a wave pattern, made a little spot of light behind that slit. Okay? Or it went through the other slit and made a little spot of light behind that slit, but no wave patterns. Okay, so they thought, wow, that changes the results of the experiment if we look and see what's going on. Looking is the same as a measurement. Okay, so then they said, let's not look, but let's leave the equipment. Maybe it's the equipment that's doing it. So you leave the sensors where they are, but you just turn off the power to what's recording the data. So now the sensors are still in place, but they're not recording anything. What do you think happens? It goes through both slits. You get a wave pattern on the other side. Okay, that's the double slit experiment. Well, that created a thing called wave-particle duality. Is a photon a particle or is it a wave? And the answer to that was, well, it's both. Sometimes it's a wave and sometimes it's a particle. It's a wave if you don't look. It's a particle if you do. And, of course, the physicists are saying, well, what does looking have to do with it? You know, this was a big problem. You know, so quantum mechanics has really kind of turned physics on its head. And that's called the measurement problem. Okay? And out of that comes, you know, entangled pairs and other phenomena that are mysterious to physicists. Okay, now there are many interpretations of why it does this and what it means. A lot of physicists have been trying. Now this was started back in the late 20s and the 30s. All of this was a big deal, and physicists were working very hard on this. They're still a big deal and working hard on it. They haven't really made any progress since the 20s and 30s, made very little real progress. And all of the theories of what does it mean, what is it saying about reality, none of them have made it into the center of physics. They're all on the fringe. I'll just talk about a couple of them. The one that's most common is called the Copenhagen interpretation. Basically what it says is that if you have a probability of being in n states, when you measure it, you just get a random value. One of those states, randomly, you get that, you measure that value. Okay, then there's one that says consciousness causes collapse, and that comes from the idea that you have to be aware, you have to measure it. Some consciousness has to take a measurement, and that causes it to collapse to the measured value. Now when I say collapse, it's a wave function. They talk about wave functions, but it's really probability wave is what we're talking about. Cause it to collapse to a certain value. Another one is called consistent histories. And that says, well, it's not random state that it collapses to. It's a state based on what happened before, what its history was. And then there's one of many worlds. And I have to mention that David Deutsch at Oxford is one of your countrymen. He's one of the foremost researchers in the many worlds area. Actually, he's published some very good work just recently on this, made some progress. The many worlds says that, all right, you have n states that it could be in. That means it's probability function. In quantum mechanics, you don't necessarily have a smeared continuous probability. There's a probability only certain states can exist. So if there's n states, he says all n of them happen. Everything can happen, does happen, except the one that happens in this reality, you know, is where we live. The ones that happen in other parallel realities, you know, we don't know about. But there is a separate physical parallel reality for every state. Well, of course, there's billions of states. Every electron has multiple states. You know, there's a lot of electrons. So, you know, there's a problem. There's a problem here as well. The problem, of course, that they had with the Copenhagen one is that if it's just a random choice, then that creates two problems. One, all of this reality that we see before us is based upon random choices. That does not compute. Also, that means that if you do the same experiment twice, you won't get the same answer. Well, physicists don't like that either. So both of those were problems. That's why I say none of these theories are problem-free. Okay, there was another one called Many Minds. It was sort of a combination of consciousness causes collapse in many worlds. And basically, it said that the many worlds weren't physical, but they were mental. Okay. Now, I didn't expect you to read this. I can't even read this, and I'm closer than you are. What this says is that there are interpretations of what quantum mechanics means down here. I have 13 of them, a baker's dozen. There's another 13 that didn't make this chart. You know, there's lots of them. It's not like there's only 13. It's kind of the top 13. And across here are different measures of quality, or different measures of the quantum mechanics event. Like, is there a role for the observer? Does it have a collapsing wave function? There are hidden variables. These are all physics terms that the physicists work with. And what I wanted you to see is basically the patchwork. There's a little bit of this, a little bit of that, a no's and yeses all over. In other words, nobody really has an idea. You know, it's just a big mystery. Next. All right, now there's other big pictures besides that one. Edward Fredkin created digital physics in 1992 when he published 2 papers. The first one was Finite Nature. The second was A New Cosmogony. And Edward Fredkin is really a pretty high-powered physicist. He was a physicist at MIT, then went to Boston University. Now he's in Carnegie Mellon. He's kind of specialized in the digital side of information theory and physics. And his conclusions were that reality is a computed simulation, that we are in a computed simulation. And he presented this paper at a scientific forum and was not received real well. I think probably didn't get a long applause. It kind of startled a lot of people. But he was a very brave man for doing that. But he had solid physics to back it up. That's why he stood up and did it. Essentially, he says our reality is digital. Time's digital. Space is digital. Essentially, it's informational. He says our reality is just information. Okay. He also said that because a system cannot compute itself, it must be computed in, his words, other. It was computed in other. Okay. He didn't want to go there where it was computed. He knew it couldn't be computed in this reality frame. Okay, so he says it came from a reality frame that's outside of our physical reality. Well, now how do we define non-physical reality? Non-physical reality is basically other, is it not? We have a physical matter reality. That's our universe. That's us. There's everything in the universe, and then there's everything else. And that's non-physical reality. So everything is not physical, and that concept's non-physical. So if this is in other, then with that definition, he's basically saying that it's computed in a non-physical. Even if you say some other physical reality that isn't physical, you know, that's cheating. It's the non-physical is what he was talking about. Now, next came Nick Bostrom, and he had his PhD from this very institution, from London School of Economics. He's now at Oxford. He was at Princeton, I believe, and he's another physicist. He's a physicist and a philosopher, has degrees in both. He wrote a paper, Are You Living in a Computer Simulation? And he just went through it logically, and he found that it was impossible to say that it was impossible. Then he found out that it was unlikely to say that it was unlikely. That left him with the conclusion that certainly almost all of us are living in a simulation. He said it was very likely. I mean, now in his mind, the simulation is done from some other physical